computing, communication, and sensing. By leveraging the unique properties of quantum bits, quantum computers can solve complex problems that are currently unsolvable with traditional computers. Quantum technology has potential to transform fields such as medicine, finance, and cybersecurity. For instance, quantum computers can simulate complex molecular interactions leading to breakthroughs in drug discovery. Additionally, quantum sensors can detect subtle changes in the environment, enabling advanced navigation and monitoring system. As research advances, quantum technology is poised to unlock new possibilities and transform the way we live and work. Its potential impact is vast and ongoing innovation will be crucial to realize its full potential. As some of you may be aware, the market for quantum technology is rapidly evolving. As of 2024, the global quantum technology market is estimated to be valued at $1.5 billion. Looking ahead, the market is projected to grow significantly. By 2030. It is estimated that it will reach to around $10 billion or more. In view of the great potential of quantum technology in the coming years, KSTA planned international webinar series on quantum science and technology during 19th to 23rd August. That's from Monday to Friday, every day from 3:30 to 5 p.m. This is the first series of webinar series that KSTA is organizing. And the list of experts, I'm sure all of you would have known, but still I will repeat. Today, Dr. Usha Devi Madam will be speaking on a tale of quantum information science. Tomorrow, Dr. H.S. Karthik, researcher at Quantum Cybersecurity and Communication in Poland, he will speak on reviving quantumness, 2 instances of repowering protocol. The day after tomorrow, Dr. Akshata Shanai, she is a senior scientist at International Center for Theory of Quantum Technologies, again at Poland. She will talk on quantum cryptography. And on Thursday, Dr. Prabhu, Assistant Professor, Department of Physics, IIT Dharwad, will speak on a few things about quantum systems. And finally, on Friday, Dr. Sudha Madam, Professor, Department of Physics, Kuvempu University, will be speaking on quantum science and technology, a bird's eye view on its origin and development. Now, I would like to introduce Dr. Usha Madam to all of you. In fact, she is the force behind organizing this webinar series. On behalf of KSTA, we are grateful to you, Madam. Madam is a senior professor in Bangalore University. She has guided more than 9 PhD students, and she has published more than 85 research publications. Her PhD thesis title was Theoretical Studies on Entangled Quantum Spin Assemblies Using Distribution Functions, way back in the year 1997. Madam's guide was Dr. G. Ramachandran from the University of Mysore. She has been recognized with many awards. Some of them are Young Physicist Award by Indian Physical Society in 1997. She is also visiting fellow at the Quantum Information Research Program of Professor Barry Sanders Division of Information and Communication Sciences, Macquarie University, Sydney, Australia. She is also a Commonwealth Academic Staff Fellow. She was a fellow in 28 in Bristol University, UK, and she is an editorial board member of Resonance Journal of Science Education, published by the prestigious Indian Academy of Sciences. And she has many research collaborations to her credit. on behalf of Karnataka Science and Technology Academy. With this very brief introduction, I welcome Madam once again. That this webinar series is, we have Association of Department of Physics, SB Arts and KCP Science College. Dr. Girija is there with us. Welcome to you. And Dr. Shubha is there. Dr. Sudha Madam is also there. Welcome to all the experts and faculty members who are present for this webinar. And I also welcome all the participants. In fact, some of the colleges have screened this particular webinar in a big screen, like for example in SBR Science Arts and KCP Science College. Yeah, and many students have joined on YouTube also. On behalf of KSTA, once again, welcome to you. Now, with this very brief background, I request Dr. Usha Madam to deliver our talk. Over to you, Madam.
Thank you, Ramesh sir. And I thank KSTA for giving me this opportunity. And it's a chance to interact with many interested people here. I guess it is a very heterogeneous kind of a crowd. That is, I don't know the background of the audience here, but in any case, I am going to tell a tale of quantum computation. That tale doesn't involve too many details. It is, I have to formulated my presentation to talk about some necessary content which needs to be understood so that one can kind of get interested in quantum computation. So I hope my slides are seen. Is it
yes,
seen,
yes,
shared? If there is any problem, please let me know if it is not moving. So basically speaking, if I am going to say that we have a bird's eye view of quantum computing, it looks very kind of confusing. So we, as Professor Dr. Ramesh said, it is in health, pharmaceuticals, material preparation, new molecules, and finance, and everywhere we have the hand of quantum computing, basically. So what is it that one is trying to do here is the question that I'm going to sketch a little bit, as much as possible in the given time available here. So, okay. So we know in Einstein and Bohr had debated over quantum theory for long years. Because mainly it sounded like philosophical to many people, but in time, what is called weirdness? That is, what we are used to is classical physics, and we think that classical physics where I can observe things and touch things and it is within my perception, I am fine. But as long as it goes into quantum world of microscopic, submicroscopic level, electrons and protons, photons, in such a level, the laws of quantum theory appear to throw some weird things, and these weird things are what nature is. We have to accept it, but it is like it's very difficult to accept by people, and there are so many reactions to quantum mechanics. It is Niels Bohr says, if quantum mechanics has not profoundly shocked you, you haven't understood it. And Richard Feynman says, I think I can safely say that no one understands quantum mechanics. And Erwin Schrödinger, one of the winners of the Nobel Prize for quantum theory invention, he says, I don't like it. And I'm sorry I had anything ever to do with it. That's what he says. But and then Albert Einstein says God doesn't play dice, and quantum theory has some kind of dice and it explains nature. That was the kind of complaint. I am going to not tell you more about quantum theory as such, but I'm going to give you a historical overview on how quantum computing came. And quantum computing has the quantum physics as the base for it. Based on that, how computing started. So it can be divided into 4 different things. Only theoretical foundations, that is 1900 to 1980, where there were a lot of technological aspects came, not about computing, but about varieties of semiconductors and kind of what we have as computer chip manufacturing, solar cell manufacturing, photocopying machine, and all that came as a first quantum, understanding quantum physics as such, but now we are going into quantum computing. So now in 1980 to 1994, one would term it as emergence of quantum computing, and the development of quantum algorithms, one may put it as 1994 to 2000, and then now we are in the kind of race to build quantum computers, read it as 2000 to 2024. So now let us say this is a kind of on the whole what has been done. So this I had got it from IBM website, but in theoretical foundations we have 1900 Planck's hypothesis, and this is to say quantum physics was invoked during 1900 basically, when features of black body radiation could not be addressed by our what is well known as classical physics. And then we term what are quantum laws? Can I harness quantum laws? This had led to scientific and technological breakthroughs like what I told you, semiconductor physics, lasers, superconductors, and so on, during second half of 20th century. I am not talking about that too. This was called first quantum revolution, that is termed as this. And the second quantum revolution is what we are going to kind of get an idea about at the end of 20th century, that is around 1980s after that. So it has become possible to control. In a lab, we can control, manipulate individual quantum systems and a few quantum systems. This led to what is called a second quantum revolution. And what are quantum computers that we are going to talk about? Quantum computers are the devices which perform computations, process information by exploiting the properties of superposition and entanglement of quantum systems. So what is superposition? What is entanglement? A brief ideas may be needed, but let us say we are in 1900, 1935 is what EPR, Einstein-Podolsky-Rosen, posed as a threat to quantum theory. Einstein did not like quantum theory as a theory. Don't call it a theory, is what he would say. So though it works well, it's not a complete theory, is what Einstein would say. So this continued, and Einstein's thought experiment, there was a thought experiment that was suggested in the paper by EPR 1935. This basically had what is called as entangled systems, basically. This was recognized, named, and used later on. So 1964 Bell inequality, but Bell inequality kind of decision between two theories. One is a classical based theory, quantum theory. Based theory is favorite to Einstein. Quantum theory is what is put across, which is that nature obeys, is what one has to say. So nature would find that Bell inequality, when it was proposed, that is in 1964. So we have 1970, birth of quantum information theory, how to process data using quantum laws. And there was a first conference on physics and computation in 1980, and IBM recently celebrated 40 years of this first conference on physics and computation. And then we keep on going now towards the race to build quantum computers. So this is here in the last line. We have what are all the computers that have been built and what is going on now, just to indicate it to you. So now let me move on to next slide. So to indicate, this is in 1930s that von Neumann, a Hungarian mathematician and physicist, he had developed how to use quantum mechanics. That is developed the basic mathematical framework necessary to understand quantum mechanics and use this language of mathematics to develop other applied aspects and check whether the theory is correct and so on. So his work included what is the development of formalism of quantum states and operators mathematically. This provided a rigorous foundation for understanding the behavior of quantum systems. So for Neumann's contribution, they had underpinnings of quantum mechanics. These were essential in paving the way for the development of quantum computing. So let us go next. So 1 minute, just it's not moving. All right. So then another theoretical physicist, Paul Benioff, he had constructed what is called as quantum Turing machines. Turing machines were there earlier. This is for a classical computer. What should be a model for classical computer? What is expected from a classical computer? So Paul Benioff formulated what is a quantum Turing machine, and he published a paper in 1998, and in I think 1985, Daesh, I think there is a error here. I have to check it. I think this is 1978. Okay, so let me check it. And in 1985, David Daesh, British physicist, he introduced the concept of universal quantum computer. What is a universal quantum computer? We have to say that it is I have to have every physical should be able to every process that exists in nature, anything that happens in physics, let us say I have a dynamics, that is I have laws of dynamics. So quantum laws will give me how is a state, how does it move from one place to one time to another time and so on. I have dynamics. So such a dynamic should be simulated in a computer. So that can only be done using a quantum computer. A classical computer, a classical Turing machine is incapable of developing such a thing, is what was noticed. And that's what is the Daesh's statement here. A crypt sentence. The existence of a universal quantum computer Q implies that there exists a program, that is, I have an algorithm, I have a mechanism for each and every physical process. I can simulate what happens in nature on a system. So that will help me to do things faster and get used to what are the new things to be checked. So the concept of quantum computing began to crystallize. Researchers started to explore the development of what are logic gates, what are building blocks of quantum circuits. That is, I need to build circuits and I have to have logic gates. So like in classical kind of computers, you may have a NOT gate, you may have a kind of other gates like changing the sign of a bit and other things. But quantum gates allow you to have what are called as superpositions and what can give you entanglement. So these are classical gates also. It's like a NOT gate, bit flip. It changes 0 to 1, 1 to 0. We are going to talk only about binary digits 0 and 1. That's the basis of a digital computer with binary digits. So if I have so many such binary digits, 0 and 1, say 50 of them or 100 of them, I have a whole system of such zeros and ones. And how do I process such a information is what is going to constitute computing for me. So I have gates which will be added into a circuit and we will have to do the processing. So now this is physics computation conference. This is FISCOM conference was held in 1980 and IBM had celebrated this after 20 years. So this is from IBM Quantum. So this brought together physicists, quantum computer scientists, mathematicians, and to explore potential applications of quantum mechanics and computation. And Richard Feynman had delivered a seminar at his first conference, emphasizing why quantum computers are to be built. Quantum principles should be used to simulate nature. That's what was the idea. And actually, Feynman says nature is not classical. And if you want to make a simulation of nature, you better make it quantum mechanics. So now the question is, what is a simulation? I need to do a simulation based on my program or an algorithm. So can I build an algorithm to simulate nature entirely? Classical computers will not be able to do, is what Feynman had seen, and his vision said we have to build a quantum computer. These were theoretical concepts, and how it could be is what one should see. So it happens that non-trivial quantum problems cannot be solved analytically, and so one has to resort to simulations on any digital computer. So now, I don't want to waste my time sitting on and keeping on doing a calculation, like how a calculator helps me to do little arithmetic calculations. I need to have a computer to give me the results so that I can go one step ahead and think about the next possible issue and next research level in for simulating nature, by getting the results of such simulations. However, this simulation is not efficient if you use a classical computer. This simulation grows unreasonably fast with the size of the problem, but such problems can be simulated in a quantum computer. Classical computer cannot be done. This is what Feynman had mentioned. And now we have, again, these are all some kind of maps which I am showing before I come to really kind of tell you the mainly entered into the story. So now basically we have initial stage problems which posed some theoretical algorithms basically for simple problems. I won't explain what is Deutsch algorithm. These are years during which they formulated. These problems are not physics problems, but for a computer science, computer theory, these are algorithms which will tell you that classical computer will not be effective, quantum computer will be effective. That is how good it will be. If you implement these algorithms and solve them. That could be seen only by checking what is the algorithm itself, how fast it is, etc. So now then came in 1994 to 2009, we have a qualitative change state. These are quantum for problems where Shor's algorithm came, which I will talk in little detail, and Grover's algorithm, that also I will talk. These were kind of path-breaking kind of algorithms which made us sit and look into what is quantum computing and how we should be ready for kind of grabbing such an opportunity. So then we algorithms for big data environment where you do get finance, health, drug development, all kinds of things. And these are algorithms developed. HHL is named for Harrow, Hasidim, and Sethloid. This algorithm is for solving a set of linear equations, but using a quantum computer. And quantum machine learning algorithms were also developed from 2009 to today, actually. And then we have some kind of quantum algorithms in the what is called as noisy intermediate state quantum era. We are in noisy intermediate state quantum era now, where we have quantum computers, but they are not error free. So to make a fault tolerant computer state, this kind of computer, even with them, I can have a classical computer and also take whatever classical computer can do and feed whatever is really crucial only to quantum computer. This is what are called as hybrid quantum classical algorithms. These are developed, and one is, this is variational quantum eigensolver, which is very important for chemistry problems. And this is quantum approximation optimization algorithm. Both are, these are hybrid quantum classical algorithms. I am only showing you names and years during which they have been formulated. Nothing else. This is not going to give you much of, this is just to give you some kind of newspaper reading experience on quantum computing. So let me now come to what makes quantum computing very different. You might have heard, I don't know the exposure, what you have heard about quantum computing, but basically everybody starts with bit versus qubit. So we are all used to what are binary computers, digital computers, where I have, let us say, the transistors, semiconductor devices, or whatever are used in today's computers. We have voltage pulses, then I may say on, off states of a voltage pulse, let us say. So on is one is called off state, I have a binary bit. This is classical bit, and this game changes when I have a quantum computer. And in today's realm, the processing and storage of ones and zeros of classical systems, this gives way to qubits, for which I have to apply quantum laws. So classical laws will cease to work, and I need to know how quantum theory indicates what is changed from one state to another, how it goes, and what all can be done, what is possible for developing a technology. So qubit is a fundamental building block of quantum computation, basically. And if I say, what is a qubit? I will say, if you have studied quantum theory, then a bit of data is presented, say, just to introduce, if I have a single atom which is in one of the two states, or let me say electron is in one of two possible states, say ground state and one of the excited state. I'm only focusing on two states of the electron. You may say there are other states also, but let me say that I don't allow the electron to go from ground state and first excited state. I'm only focusing on two states. So such a thing is 0 and 1. I will call those two states as 0 and 1. And a single bit of this form is known as a qubit. A qubit is possible, I can prepare what is a qubit in a superposition state. That is, quantum theory allows you to have 0 and 1 in a combination, special combination, which is not possible in classical theory. So particles cannot be in combination of being here and being there together. So, but 0 and 1 are voltage pulses. You can't create them in superposition, but a quantum bit it's a different, entirely different process where I create a quantum bit and I make use of what is how to do algorithms and apply gates and all that. That is coming from quantum theory, basically. So with that, let us move on. Let us say, I will is a different thing, but if I have to say, the basic advantage of quantum computers is what is called as quantum parallelism. What is quantum parallelism? Let me say, in a classical computation, I have a data unit bit. Bit is 1 or 0. So valid states are x is 0 or 1. So that's all I have. So I have two kind of stations where 0 is stored or 1 is stored. I will access 0 or I will access 1. That's how I work. But in quantum computation, I can have 0 and 1 in superposition. This is a possible. That is, quantum theory tells nature can exist in superposition like this. So I can have this possibility of a superposition. In other words, a classical system, classical computation goes in step by step with using zeros, ones in so many steps, but a quantum computation can happen sequentially. It will happen, keep on doing it parallelly, and several classical computers appear to be working together in a quantum system. So that gives you additional speed and how to make use of. So now, again, I illustrate a little more on what is a bit and a cube. So I say, if bit what is a bit? This picture shows you that you have a 3-qubit system. In a 3-qubit, I will have 101 or 000. That is classically, I may have 3 bits, all possible bits you will write. That is 2 to the power 3, which is 8 possibilities are there. And a quantum can come with all of them in 111 get. That is, I have a state and all these we put in superposition. So I need not have to look at each one of these, but do things together in a quantum thing. So this is each quantum bit is, it has, if at all I have 3 bits, 3 qubits, then the number of the system size is 2 to the power 3. If I have 4 quantum bits, qubits, then the size of the system is 2 to the 8. Sorry, 2 to the, okay, if I have 8 bits, then 2 to the 8. So this power of these qubits is the inherent ability to scale qubit system. The scaling, what is the number of possibilities? It to the power 10. This scales exponentially. That is what, because of quantum superposition. So I have, that's what I mentioned. So if I have various, this is 2-qubit system can exist in all possibilities. Again, a picture indicating it to you. And I emphasize once again that a n-qubit system encodes 2 to the power n numbers basically. That is, that many numbers are there. And then I have, if n is 50, you may check that 2 to the power 50 is around 10 to the power of 15 possible states of the quantum machine, and this number exceeds what is the capacity of a largest conventional classical computer, supercomputer. So if I have a 50-qubit system, the possibility of states is much more than a conventional classical computer. Only what is quantum computer made of? I need to depend on how do we have a qubit generation. So we have different platforms. So platforms being ion traps. So I have a few ions. Let us say ions have their energy levels. We choose a specific ion, and then there are excitations, de-excitations only in 2 energy levels, and several such ions are put in a arrangement and we have trapped them. And such a trap can be, that is possible to work as a quantum computer. I can operate on it, and there is which can also give you a computer, and optical photon computer where photons, entangled photons, photon states can create a quantum computer. And we also have some solid state, what are called as superconducting systems, which are what IBM is putting across. Google, IBM, they have all been working on solid state systems. So this is what we have. And the possibilities are several, and while one has to try how to make them, bulkiness should be reduced, and which turn out to be the best uh, available quantum computer, it will be decided in, let us say, hopefully, say, in a decade or 2. But we have possibilities, there are several. And given a quantum system, what are the resources? That is, I want to go to a shop and buy things, I will use my currency. So for quantum computation, the currency is what are called as quantum superposition. If it is not there, I cannot do quantum computing. And if there is no entanglement, it is not possible. So these are currencies for us. And then we will count what are the currencies, how many are needed, what is the cost of my computation, and so on. So what is superposition? I mentioned that two states can be in same place, etc. And what is an entanglement? I need more than one quantum system. If there are 2 quantum systems and if they are entangled, say the word entanglement, it is the ability of quantum systems to exhibit correlations There are correlations. If something happens, measure one and the other will always correspond. That is, there is a response from other side also. Lot of theoretical things go in here. I am not going into the details, but still I will just mention a few things. What is quantum entanglement? You may look at it as a clever superposition. That is, if I have a superposition of single system, that's one thing. If I have superposition of, let us say, two-party systems or a three-party quantum system, then I do have different Hilbert spaces and different houses for each of the systems, but they are in superposition. Which is the other particle in the other may be, its properties may change because of what is quantum laws and nature obeys it is what we know today. So it is something like what I have here, a set of gears which move with the invisible control here. So this is up, this is down, kind of a thing can happen. And Schrodinger had said, I would not call it one, but rather the characteristic trait of quantum mechanics, that is entanglement. The one that enforces its entire departure from classical lines of thought. What we are highlighting here is the new theory which has to be learned afresh for doing computation, for learning any other, to understand nature. This particular theory is completely, there is a departure from classical lines of thought, and we have to go beyond our perception to go ahead with it and do much more technology. So now, when you have two photons, opposite polarizations, let me say I have a photonic qubit, that is horizontal photon and a vertical photon. One of the photons, photon number one is horizontally polarized, photon number two is vertically polarized, but there is a possibility of superposition between this one, and when photon number one is vertically polarized, photon number two is horizontally polarized. This is not possible in a classical system, but I can create this because it obeys quantum rules, and nature says that I do obey quantum rules. That is when it comes to photons and other electrons and so on. So at the instant the polarization of one photon is measured, you don't disturb the other one, measure one of the photons, the other polarization becomes immediately fixed. I didn't touch it, but it gets fixed. So no matter how far away it is. So with that, I will now just mention, this is a nice quote that I found. Just a minute. I don't know if it is seen. It is here. Is it possible for you to read the quote mentioned here? When two systems are entangled, is it fully seen? Anybody? Am I audible?
Yes, you're right.
Yes, madam. Yes,
Can you
madam.
see the screen? This is a quote by Professor R. Simon in a resonance article, which is in 2002, when we were all discussing, that is, they were discussing about what is quantum computation, how to understand it, etc. So it is what Simon said was, when two systems are entangled, the state of the combined system is more pure and less random. That is, it has, pure is not a word from English, but there is a mathematical content in it. It is less random. Its entropy is less than the state of either system by itself. I am trying to explain entanglement through something that I can try. The whole system of entangled system that is more ordered than its subsystem. If at all I look at a classical system like that, classical probability theory, where I can check that state of the subsystem is more ordered than that of a bigger system. So what Simon said is, a book written in an entangled state. Suppose imagine that a book is an entangled state, then I will have to grasp the book in its entirety as one unit and not sentence by sentence, or paragraph by paragraph, or rather it is something to say that I don't have bits and parts telling me whole story. Whole should be learned from the whole. That is, it has the entire. It is more clearer to read it as one whole grasp. So in this sense, he says, book has to be grasped in its entirety. In this respect, an entangled state is like a good piece of art, is what Professor Simon said. I liked it, so I put it here. Now I come to what is kind of quantum algorithms and how do we understand what is going on, basically. I take two examples to describe it. Again, in common terminology, that is, let us say I am doing some puzzles. What is the kind of challenge to me? I want to solve a puzzle with my time and effort should be minimum, but I should win. That is the goal for me. I want to try to do it and I did it quickly than somebody else. That's the motivation when I solve a or a puzzle. Now let me pose one particular problem. Before that, let me say, if at all I have a puzzle which involves too many steps, I get tired. Let us say I have a whole lot of books and I have to sort it. If I ask a young student to keep your books sorted and ready, I will come and check. They will give lot of excuses not to do it, that because it takes too many steps to do and to keep it in order and so on. So, and I have to memorize, that is sorting and all that. Human mind is not very efficient in doing this. We go to computers when it's needed with too many huge data sets and all. So now the question is, depending on how many steps are there in a particular task and how much time and effort I get a solution for the particular problem. This is what is thing that I need to understand. For that, let me say one particular problem. So in quantum algorithms, we first think about what is a computational complexity. Is it faster? Is it less resources are used? I can use less resources. These are my guidelines for talking about efficiency of an algorithm. So what is my hardware? How do I implement it? All these things play a role when I have to think about complexity involved in a particular problem. And also, some problems are solvable, some are hard, some problems are non-polynomial, polynomial. That is, they mention you how many steps are needed for problems. So I am talking to you the kind of language of computer scientists, algorithms which are going into different cadres, that is polynomial, non-polynomial, exponential, that is depending on kind of the depth of the algorithm and so on. With that, now let me say what has been shown. A quantum algorithm, some of the quantum algorithms can turn what are exponentially difficult, exponential steps in a classical problem. I'm talking about it. I'm not showing you how it can be demonstrated. So if I can convert exponentially kind of problem, exponentially hard problem into a polynomial problem, I achieve some amount of relief. So I have to look at what is an exponential problem, what is a polynomial problem. So execution of time depends on exponential goes like this. This takes lesser number of time. So that is what is the idea. Now I come to a particular algorithm, that is Shor's algorithm. I'm telling you what Shor did to prove what is Shor's algorithm. Let me first, in the first step, let us understand what is Shor's algorithm. Now, first thing is, let us say I ask you to factorize one number. I give you a number which has two prime, prime factors. Let us say 91 is 13 into 7. If I give you 91, your job is to write it as two prime factors. So this is like factorizing a number. Now the question is, if I take what is called as a huge number, which I have created by multiplying two huge prime numbers. I take two prime numbers. Multiplying can be done easily using a classical computer. I generate a huge, say some 100-digit huge number, and I ask you, split it into its prime factors. If you don't tell me which factors you used initially, a classical computer will say it is very hard. So this is a exponential time problem for a classical computer. So Peter Shor wrote an algorithm using quantum rules, quantum and so on. And what he showed was best classical algorithm is exponential, but a quantum computer can do it in a polynomial time. So what I have shown here is time is exponential with classical and time is logarithmic. That is, it will be lesser time. That's what is shown. So this is in 1994, beginning of when you see that there is one particular problem, that is factorization of prime numbers. How is it so important, you may wonder. I will try to tell you how it becomes important as I go on. So I will, let me just see that this is a picture that is I have picked from a proceedings of this mesoscopic superconductivity spintronics in 2006, which mentions how execution time to factor a large number on classical and quantum computers. What is there? Suppose I take 104 PCs, supercomputers, and in tandem they are all together grouped network, and I try to factorize a number. It is exponential, fine. But if I have 104 pieces put together and I am trying to do it, how I go is shown in this particular line. So that is it 1 second? Is it 100 seconds? If I have the number, my bit size is 100. That is, if I give you something which is 100 bit size, it will take, let us say, less than 1 second. But as I go on, there is a point where it takes 1 year, 1 month, and then it goes into 1 billion years. It is age of universe. You can't solve it in real time. That's what this particular curve shows. And the what is used here is what is called as, just a minute. So this is NFS, that is NFS is, just a minute. This is, I didn't mention it here. So the left curve has one NFS number. Your bits is, let us say, 100,000, 1 billion. So it takes so much time. With the clock speed increasing, it is going to be, say, 1 year, 1 month here. So it will be very, very efficient comparatively. Have we done it? No, we don't have so many quantum computers with that many qubits yet, but these are predictions. Even this particular one is a prediction with up to, say, 1 year, 1 month, I might have done. So this is speculations. This is a performance of 530 bits. Okay, there is a question which I will address later. That's not about what I'm trying to talk now. What are flux qubits? What are something? It's a detail about one particular physical platform. But my attention is given for what is it that we are doing. Okay, so let me try that. So here I have a 530 bit number. I have 530 classical bits and such a large number, a classical computer, which is 104 supercomputers and workstations, in 2003, it took 1 month. But if you have a quantum computer, same thing could be done using a few minutes. So that is what is the picture. That is, and then you extrapolate it and say, if I have Moore's law, maybe I will be able to use less number of computers as the years go. And then if I have 100 pieces in 2018, that covers the 10,000 pieces in 2003, then I get this kind of a curve. All these are speculations. But now if you want to see numbers, then bits, factoring in 2006, it will take 10 to the power of 5 years. These are speculations. So factoring of 2042, 10 bits in 2042, these are speculations. With a potential quantum is what I want to give you an idea by looking at data. So now let me tell you what is big in factorization of prime numbers. Let me say there is, you all know about cyber security. I want to protect myself from online security, that is online threats for my online banking, emails. I don't want somebody to hack kind of things. There is cyber security. I just want to give you very general ideas here. So there is a patent, US patent, which is in 1983 called RSA encryption, that is Rivest, Shamir and Adelman. They had a public key crypto system based on prime factorization. Let me emphasize once again, I repeat. So suppose the encryption means, so no, I give you a huge number which is multiplied using 2 prime factors. I know which 2 prime factors are 2 prime factors. A classical computer will not be able to do it. You will not be able to solve that. That is a huge number. You cannot do it at all. So in such a case, that becomes a good encryption. So RSA encryption is employed for online security when using web browsers, emails, online banking, and any site that begins with HTTPS. That is, I want to have my data secure. And quantum computers can break RSA encryption. That is, quantum computers use only polynomial time to break whole large number into 2 prime factors, as I told, using Shor's algorithm. So, but no need to worry. Right now, you don't have to worry because quantum computation is still in its infancy. So RSA protocol still works for us, but we have to be ready when we need to have good security for our data. We need to have encryption systems that are quantum proof. That is, I should have no security threats when we have quantum machines also. So those are things. So now again, I emphasize RSA 250 is a code for 10 to the 250 digit number, whole number. So classical system will take 3000 years, but a quantum will take minutes. And RSA 600, it is so huge a number, it will take so huge number of years, but this is in hours. So that is the kind of estimate which plays its role in cyber security. So now let me now go to another which made big difference to quantum computation. This is called Grover's algorithm. Remember, I'm telling you a story, some stories. One is factorization of a huge number into 2 primes. That is a quantum algorithm, is Shor's algorithm, which showed the difference between factorizing using classical computer and factorizing using a quantum computer. Now I will tell you one more. It is called Grover's algorithm. What is it? That is, I will explain it in my own way. So think of a telephone directory. You have alphabetically ordered names and you have telephone numbers. So if you want to check somebody's number, you will go alphabetically. That is easy to check it. So now suppose I have reversed the telephone numbers first and order of according to telephone numbers, names will appear. So this is called unsorted data. I don't have a sorted data. Alphabetical ordering is sorted, but number-wise ordering of telephone numbers is not going to be sorted. So suppose I have an unsorted data, then how am I going to search for one particular number? That is, I want to call a friend, I want to check through telephone directory, but my telephone directory is unsorted. It gives me numbers. I have to keep checking, is it this one? Is it this one? Is it this one? So on. So I have to have n tries. Let us say n is 1 lakh, then I have to do separate trials in a classical computer. That is the algorithm. This is in 1996, and this is database search. For an unsorted database items in storage, it takes an average number of square root of n searches. So that is, quantum computer can do searching one particular number, let us say, desired, but I am given, let us say. So root of 1 lakh is much, much smaller compared to 1 lakh searches. A classical computer will take n steps, but a quantum will take root n. Let us say if it is 1000, then root of 1000 is only 100. So I can do it with 100 steps. So this is the advantage of quantum computing for a particular system. Why it becomes different is I have made use of quantum laws to give you this kind of algorithm. Is this physics? I will say, please understand, we are using laws of physics, quantum physics, to make computation. So for computation, I need to know what is the information, how to use it, how to process it. For that, we have these algorithms, and what are all its applications is our next step. So now let me say one more, make it little more clearer to you. Let me say what are called as combinatorics calculations. In general, let us say I have a calculator, then what I will do is play some arithmetic calculations. It makes my life easy because I don't have to check what is the bill, how much I have to pay, and what is multiplied by what. I don't calculate it by my handwritten things. I use a calculator. Like that, there are several things a classical computer will do. Let me illustrate what is a combinatorics calculation. So what I do is combinatorics calculations deals with finding, let us say, optimal arrangement of items. I suppose I say I have a set of items. So let us say 100 items are there. I can arrange them in different ways. But let me say there is one particular arrangement which wins a particular task. Task has to be specified first. I have to specify my game is this. You choose this particular arrangement given a set of 100 items. So this is called, I want to look for an optimal arrangement for a given task. That is combination. Classical digital computer, what does it do? Take all these items step by step. It arranges it in one way and checks if it is efficient. If it is not, it throws it and takes one more set and does it. So this is number of steps involved are n there. But a quantum computer is capable of calculating all possible arrangements in one step. It is parallelly it can do, and it removes wrong answers instantly at that moment itself and settles on the best arrangement spectacularly faster. That's the advantage with combinatorics calculations. That is what quantum laws allow you to carry out. Now, how do you think of commercial applications of doing combinatorics calculations easily? So now let me say commercial applications. In chemical and biological engineering, so engineering, I have natural systems and I have engineered systems. So engineering, chemical and biological engineering deals with discovery and manipulation of complex molecules with exponentially large number of configurations. A molecule has huge configurations and I want to check which is the optimal arrangement which gives me, let us say, least energy or something which is, that is a task is decided by me for a particular program. So which is the good optimal arrangement of molecules? Hello. So identifying an optimal molecular configuration for a particular goal is a combinatorics calculation. That is, you may put it in an overall way as a combinatorics calculation, and this can be carried out faster by a quantum computer. Now, with this, it will be possible to engineer new molecules. You may engineer, that is, using this possible engineer new molecules so as to recognize different optimal molecular configurations, that is, which is not possible with already existing molecular configurations, and the new optimal molecular configuration may win in a particular drug design or material design, and this will help in effective drug developments and new materials and all that. So then, as I told you, in cyber security, again for encryptions, mainly classical encryptions have been combinatorics calculations. And if you want to do better, use quantum encryption schemes, because a classical quantum computer can break whatever are combinatorial calculations easily. So you have to go for different and cryptography schemes. So such schemes are there. What I hear is some banks and companies have already kind of using quantum cryptographic systems for their security, but this is huge systems, extraordinarily expensive, so we cannot still have them in our security systems, but it is going to develop, and we are going to have better situation where we need to depend on cyber security using quantum computers. So now, financial services. Again, finance was one of the earliest domains to embrace big data in class computation. So much of the science behind pricing of complex assets, that is stock options, if you get a few seconds early, you will get huge profit. So if you can make it using a quantum computer, why not? So your estimate of what you can do, how to have a good stock market dynamics. So you may need for financial services, you will have combinatorics calculations which can be done easily with quantum computer. So this is just a commercial applications indicated to you. And now I don't know how long I can go. Dr. Ramesh, it's already 1 hour. So
Madam,
shall I go for 10 to 15
yes, ma'am.
minutes more?
Yes, ma'am. Yes, ma'am.
10 to 15 minutes more.
Yes,
So
ma'am.
this is, now I am just indicating to you how to write what is called as a qubit. A qubit circuit symbol is this. In quantum computation, I need to use a symbol, develop a symbol, and then put them together and create a quantum circuit. This is 0 qubit, which is quantum mechanically written as ket 0, and it is a column 0 and 1, like this. It's a matrix, column matrix, and 1 is this. And what is called as a Hadamard gate, which I mentioned earlier, didn't say anything. A Hadamard gate can create superposition of 0 and 1. It's a matrix like this. It creates superposition. If you feed a 0 as an input, 0 is 0, 1 column, multiply Hadamard matrix on the 0, 1, you will get 1 and 1 here with a 1 over root 2. So that is 50% of the time it is 0, 50% of the time it is 1. And such quantum gates possible, they exist. And a rotation gate can be created, and there is something called as a controlled NOT gate. What it does, I will tell you. So that is, controlled NOT gate can create a entangled 2-qubit state. So with the appropriate design. So now let me go ahead to tell you what is just in between to say what is a single qubit state. It's a superposition of alpha and beta. Now 2-qubit state is a superposition of all possibilities 0, 0, 0, 1, 1, 0, 1, 1. So that is written as a 4-componental column. Now what does a Hadamard gate do? Hadamard gate is written like this, and it will take, if you apply Hadamard gate on 0, it will create a 0 plus or minus plus 1. If you have a Hadamard on 1, it can create a 0 minus 1. So circuit symbol is this. Similarly, I told you 2-qubit states and what is entangled state. So a Hadamard CNAT gate can be useful for creating entangled state, and I am terming something as Bell state. I have not explained what is a Bell state, but name of the state is Bell state. So the CNAT gate, what does it do? So I have, before I feed it into the circuit, I have a control system, I have a target system. Both are quantum systems. 0 qubit, and afterwards control will be 0, target will be 0. But if the control is in 1 and target is 0, depending on control is in 1, you do get target flipped here to 1. So 1 0 becomes 1 1. But 0 0 will not happen, nothing happens to it. 0 1, nothing happens to it. 1 0 will become 1 1. 1 1 becomes 1 0. So this creates possibilities of creating a entanglement. So now to see, just as an exercise, if I have an arbitrary 2-qubit pure state is written here, and what I not get to 0 0 will be 0 0, 0 1 will be 0 1, but 1 0 will become 1 1, 1 1 will become 1 0, because that is flipped. Second, that is control, whatever is the target bit will get shifted. So now how do I create an entangled state? A entangled state. Oh, my slides are not moving, is it? Hello?
No, madam.
I am
Moving.
moving.
Yes, madam.
Do you see Hadamard gate slide?
Yes, madam.
Okay, fine.
Yes,
So
yes.
some message came which said slides are not moving. Then I got worried. Okay. So now let me say
The
what
slide
is
number
the
is 37,
entangled
madam. Is it?
Hello?
The slide number
Okay.
is 37 now.
Right. I have a few more. Let me rush through it. So I have construction of some state like this. This is what I want. I have in quantum computation, one uses words like Alice and Bob share 2 qubits. So their qubit system is, let us say, Alice is in 0 qubit, Bob has a 0 qubit, or Alice is in 1 and Bob is in 1. It is like a horizontal vertical polarization photonic qubit kind of a thing. So this is called a Bell state. Why Bell state? What is the history? I am not talking, but I am telling you that this is an entangled state, very useful in quantum computation. Let me construct it using the gates that I mentioned here. So in order to construct 2-qubit Bell state, phi plus AB, I will take 0. One of the qubits is in 0. Take it and feed it to a Hadamard gate. What does a Hadamard gate do? It creates a superposition of 0 and 1. Now I have I have a B also. So I do get what is states plus A. So I mentioned, okay. Okay, there is an error here. 0A plus 1A and 0B are sent. And now I will send it through a CNAT gate. Okay, this is difficult to explain, but you have to first do take 0A, feed it to Hadamard gate, and then the other state is simply 0B, and I will take this particular combination 0A plus 1A and 0B to CNAT gate, where A being the control bit and B being the target qubit. This is the exercise that one has to do to check what is the output of a CNAT gate, that is an entangled state. So then there are some particular calculations which I will not detail here, because my idea is to do some kind of a overall on why we are doing quantum computation. It's a tale that I am kind of summarizing here. So, but some simple calculations are going to be like this to learn what can happen when I want to create what is a Bell state. Now, thing is, I can create any quantum circuit, bigger quantum circuits, using only the gates that I showed you. There are a few 1-qubit gates and a few 2-qubit gates that can give you a universal computer is the claim. There is a theorem. So I can learn these and put them together and play with them, construct an algorithm using this and operate it. So that is the way one has to progress, but one has to know what has been done and what is a quantum kind of circuits and algorithms. So we can create different well states if I know how to put them together and calculate what I get. So this is the create states. Now let me tell you one more. This takes 2 minutes for me. Let me say I have quantum technology also addresses a question of, can I send some information from one place to far away place? This is like sending information from one place to far away place. How do I send it? Now let me tell you, this is basically like copying in a classical system and sending the copy, keeping a copy with you. That is, I will now ask a question. Can I have a single copy of the state? A state, quantum state, is a source of all information for me. Can I make a copy of it? This is multiple copies of a same state. So that is like if I have a blank state and a state like this, through a photocopying machine, I can have psi together. But this is not possible. I won't explain why. This is mathematically, I have to take some time to explain. 1 hour 15 minutes is not enough. But let me tell you, psi gamma cannot become a psi. That is what is called as no cloning theorem. Now question is, quantum machinery forbids Alice to read her qubit explicitly and send information to Bob. Let us say Alice and Bob are in faraway locations. They want to send information about 1 qubit, let us say. Can she send it? Can Alice send it to Bob? She cannot even check the qubit. She has to transfer it to Bob. So in such a case, what should I do? So way out is what is called as quantum teleportation. And what is teleportation? Again, without telling you details, I will just mention that send information about unknown qubit which can't be cloned, and I can't make multiple copies, factory of a qubit, and keep on sending unknown qubit to everybody. But I will use what is called as a scheme called quantum teleportation. So how do I explain it? Let me say I have a cartoon here. What I take is Alice has a yellow photon. Imagine Alice has a yellow photon and Charlie has a pair of blue photons. Alice doesn't know that she has a yellow photon, but she has to send that yellow photon to the place far away location. What is the kind of technology that she has? So a supplier Charlie who has 2 blue photons, he gives 1 blue photon to Alice, 1 uh, blue photon to Bob. Alice's system and Bob's photons, they are entangled. So what I am saying now, there is a yellow photon which needs to be sent to far away location. Bob is in a far away location. Alice has to send. She has a yellow photon and she has a blue photon which is entangled with Bob. With the help of Alice's new blue photon, what can she do is the question. Alice and Bob's relationship is cordial, but they are far away. So what Alice does is, she puts the yellow photon and she puts her blue photon together. She doesn't do anything to yellow photon, but she puts them together and do what is called as a quantum measurement. With such a quantum measurement, it so happens that quantum theory allows you to have what is so called, what was before is photon, it becomes a yellow photon. That is to say, a yellow photon which was with Alice will reach Bob's end by Alice doing something called as a joint measurement on her photon with the yellow photon. It automatically converts what is Bob's system into a, from blue photon to a yellow photon. This is the story of teleportation. It only says what happens to A will always affect B. This measurement that Alice does here, it will affect Bob's system. It becomes yellow now. So I can transfer what was the information using quantum teleportation. That is, it is faithfully transferred. So now this idea was developed in 1993 by Charles Bennett, and you have quantum teleportation realized experimentally in 1997, and it was used by photons only, and several such results are there. Today we have a satellite in China where quantum teleportation is possible from this, and these are different possibilities with teleportation. Remember, system itself is not teleported, but the information about the system is teleported. So there is this river Danube. So Alice and Bob, using microwave link, they can transfer whatever is the entangled states can be carried, and teleportation can be done. So Nobel Prize 2022 was given to three science alien allied closer and establishing what I didn't mention, a violation of Bell inequalities, and pioneering quantum information science and quantum technology. So this is known. So they did a huge set of experiments without knowing its technological significance. They just tried to play with single systems and few body systems, and they entangled several photons, several systems, and that's what it is. So this is a picture of how 150 kilometers away the laser was transmitted between two stations on each of the islands in Vienna. So this is seen here, this kind of a possibility. Now I just want to mention in the end about National Quantum Mission. So that is all over the globe. United States, Canada, European Union, China, they have made a huge head start in quantum technologies. They have managed to develop quantum computers, and India recognized its potential and impact of its revolutionary scientific breakthrough in various sectors like health, finance, drug design, as I mentioned roughly. So this is on 19th April 2023, India has announced its 6,003 crore national quantum mission for next 8 years actually. 2023 to 31, we are supposed to have in India, we have to have flourished quantum technology. So this India happens to be only a 7th country. There is some debate about it, 7th or 9th. This to have dedicated quantum mission like this. And India's national quantum mission has the potential to derive major advancement in technology, science, and industry, provided we have a quantum workforce. So adopting quantum technologies is no more a choice today. It's a question of getting in at the earliest. That's what Professor Ajay Kumar Sood says, who is the principal scientific advisor to Prime Minister's office. So with that, we say thank you. I will take any questions. So we have to be ready to the quantum workforce. We kind of get interested and get motivated on in quantum technology.
Thank you very much, ma'am. On behalf of KST and on behalf of all the participants, I would like to thank you very much. Such a wonderful presentation, starting from overview of the quantum science and technology to the core fundamental concepts of the National Quantum Mission. Until National Quantum Mission, you have explained everything very well. Before taking any questions, I request any participants, if there are any questions or doubts, they can ask directly or they can post it in the chat box.
Yeah.
And meanwhile, I would like to request our quantum team, Dr. H.S. Karthik sir, Dr. Akshata ma'am, or Dr. Sudha ma'am, or Dr. R. Prabhu sir, if they are with us here, they can give their feedback
Opinion, comments.
or yes, comments. Madam, there was one question from NV Raju. Can you answer on that?
I don't see it here. Will you please
Okay.
read it for me?
Yes, ma'am. Yes, ma'am. Can you
Okay,
throw
I
some?
can see it.
Can you throw
No.
some light about charge, flux, phase, orbit?
That's what I read it earlier. So
Yeah,
I don't
phase
know
to
which is in which context it is being said. So what I think it is in superconducting quantum computing. So I just want to say superconducting quantum computation, that is solid state quantum computing. I am not an experimentalist, so I may give you references, but not right away, because I don't do any work on particular physical platform. So as I say, it's a very, very broad field as already. So this is about a particular physical platform and details of physics that this person is asking. So I am sorry, I can't answer you. If there is anybody in the
from our quantum team,
audience,
if Dr. Chandrasekhar sir or Dr. Akshita ma'am, Karthik
KSTA,
sir,
yeah,
if they can answer, they can.
yeah.
Sir?
Thank you.
Yes, ma'am. Thank you, ma'am. Thank
But
you,
this
ma'am.
is not what I spoke about today, and
Yes,
I
yes,
am
ma'am.
very sorry that I will not be able to answer it, because I'm not an expert in any of these experimental things. I am a theoretician.
Any other comments from our quantum team, Dr. Akshita ma'am, Dr. Karthik sir, Dr. Sudha ma'am? And Anant Naik sir?
Hello. Actually, it was a very nice talk. We don't have any comments, but just to answer Mr. NV Raju, I think he's talking about transmon qubits, which are
Correct, correct.
how does
Correct.
one make these in on quantum computing platforms? This is
Yeah.
a hardware question. So basically, they are like LC circuits, inductors and
Yeah.
capacitors, which are put together in such a form that they form a transmon qubit. And I think
Yeah.
there are quite a bit of references for this. So
Yeah,
this is
and
all
I can also say in TIFR Bombay, there is Vijay Raghavan's team which is working on these kind of systems. So you may refer to his papers, Vijay Raghavan from TIFR.
Thank you very much, ma'am.
Okay.
Thank you, Dr. Akshita ma'am. Any other questions? Participants can ask. Dr. KV Rao sir, any input sir? Dr. Chandrasekhar sir? Karthik sir? So if there are no questions, we will formally end up the today's session. And
No, we have
tomorrow,
to have, I think, sir, we should have some quiz competition or something based on the lectures, because no questions would come. At least
yes,
they
yes,
can attempt.
yes, yes.
Some
Tomorrow,
problems.
what we can do, ma'am, some poll questions we can take from the speakers that
Okay.
can be mentioned in the chat box
Yeah.
itself. So it will
Fine,
be easy to
fine.
learn. And
Okay.
after the last session of this series, we'll be taking feedback from all the participants, so that
Fine.
it will be helpful for us to improvise further.
Right.
And
Right.
okay. So finally, if any other words or any other questions?
So I think Akshata has shared a preference for
Yes, yes.
somebody's
So our
question.
quantum team
NV Raju's
member
question.
Dr. Akshata ma'am has shared some reference
Yeah.
materials for
So he can check.
superconducting platforms in the chat box. Those who are who requested this, you can use this link. I think NV Raju sir, it will be helpful for you. So almost a 1.5 hour, we have a wonderful session from Dr. Usha ma'am. Thank you very much, ma'am, on behalf of
Thank you.
KSTA and on behalf of all the participants.
Yeah.
So this session will be recorded and it will be in the Academy YouTube channel also. Those who have missed this session, you can go and watch in that YouTube channel also. And meanwhile, stay tuned with us. Tomorrow we'll be having a session on reviving quantumness, 2 instances of repowering protocol by Dr. H.S. Karthik sir. So with this, we would like to thank you once again. Thank you one and all. So we'll be ending the session today formally. Thank you. Thank you very much, ma'am, once again.
Okay, thank you. Thanks, everybody.